Here, we are going to introduce our latest work, DiffCLIP, leveraging Stable Diffusion for language-grounded 3D classification. Large retrained models have revolutionized the field of computer vision by facilitating multi-modal learning. Notably, the CLIP model has exhibited remarkable proficiency in tasks such as image classification, object detection, and semantic segmentation. However, this efficacy in processing 3D point clouds is restricted by the domain gap between the depth maps derived from 3D projection and the training images of CLIP model. So, in this paper, we introduce DiffCLIP, a novel pre-training framework that seamlessly integrates Stable Diffusion with ControlNet. The primary objective of DiffCLIP is to bridge the domain gap inherent in the visual branch. Furthermore, to address few-shot tasks in the textual branch, we incorporate a style prompt generation model. Here, we introduce the framework structure of DiffCLIP. For visual branch, there are two stages. The first one is multi-view realistic projection. In this stage, we use Stable Diffusion to help transfer projected depth maps to a more realistic image style, minimizing the domain gap between the training images of CLIP. To generate realistic depth maps for better controlling the Stable Diffusion model, as well as to save computational resources for zero-shot and few-shot tasks, we design a multi-view realistic projection module. We will introduce this module in the following video. The second stage of visual branch is Stable Diffusion-based style transfer. To better use Stable Diffusion in our task-specific domain, where the input is depth maps, we use ControlNet, a robust neural network training method, to avoid overfitting and to preserve generalization ability when large models are trained for specific problems. For the textual branch of our framework, we design a style prompt generation module for the few-shot tasks, and we only use human-designed text prompts for the zero-shot classification task. We will introduce this style prompt generation module in the following video. This image shows the style transfer results of a monitor. Next, we will detailedly introduce the prompt generation module and the multi-view fusion block. For few-shot tasks, in the textual branch, we design this prompt generation module. In this module, we train different style prompts for each 3D point cloud. We use a frozen pre-trained point transformer as an encode, and then train a MetaNet to better encode different layer features of the point transformer. And the output will be embedded into the final style prompt. After we get the outcome of CLIP encoder for both visual branch and textual branch, the feature of these two models will go through this multi-view fusion block. In this block, we calculate the cosine similarities between image vectors of multi-view and the text vector. After we get the cosine similarity, we can do the classification. Next, we will show some experiment results of our work. In this table, we show the zero-shot classification accuracy of DiffCLIP on ModelNet 10, ModelNet 40, and ScanObjectNN dataset. Without any 3D training data, DiffCLIP achieves an accuracy of 43.2% on Object BG of ScanObjectNN dataset, and it reaches an accuracy of 82.4% for zero-shot classification on ModelNet 10, which are state-of-the-art performance. In this table, we show the few-shot classification accuracy of DiffCLIP on ModelNet 10 with different shot numbers. We compare few-shot classification performance of DiffCLIP to PointNet and PointNet++ in terms of k-shot classification accuracy. As we can see, DiffCLIP surpasses PointNet in performance and approximately approaches PointNet++. It reaches an accuracy of 79% under 8-shot training. That's the end of the introduction of DiffCLIP. Thanks for your listening. Code, data, and supplementary materials are available at this link.